How's it going, everyone? Doing all right. Getting through the week, you know. We're in that part of the semester where we just have to keep at it and keep going. How's the Tuesday, Thursday part of this class going? Y'all doing okay in there? Yeah, it is going by quick. I'm probably a little behind in a lot of my classes, but it's okay. Sure. Sure. What are you trying to do on your calculator? When you divide, does it write it as a fraction still? Yeah. What you need to do in that case, and this is on my TI, and if you have some kind of mode function, it might be that you're set on math print and you need to be on classic. This is on the TI. Maybe slightly different on the Casio. But like the TIs use this math print thing. Like when I turn that on, if I do 5 divided by 8, well, no, I didn't do it right that time. No. But anyway, what happens is the mode that it's in is basically not giving you the number the way that you want it when you get an answer. I don't have a Casio. I have a Sharp. I think this one's old enough that it's not going to have those issues, though. I don't know. If you want to try to take a picture of it and show me like the face of the calculator and the buttons, I can try to figure it out. I can't guarantee anything without being able to hold the calculator myself and work my way through it, but you might also do a Google search. It's probably just the mode that it's in where it's not giving you an answer. Yeah. Yeah, this is where it's nice to have face-to-face classes. Just figure out key details such as this. Usually on the TIs, that's a quick fix because eventually I figured out that it's just the math print option on the TIs that students are having trouble with. It accidentally gets stuck in that mode, however that happens, and then from there they just it doesn't give them the answer in the format that we wanted it. Any other questions you'll have or concerns about business math in general, or this course or the other course? Yeah, like, did you have a specific example you want to look at, Caitlin? Mm-hmm. Like that? Close enough? Okay. We'll go with that. Okay. So what I would recommend in this case is we just focus on what this value inside the parentheses is. We can deal with solving for R as a secondary um, focus in this approach. Um, so for starters, we always want to work inside out when we're working with these calculations. So the very innermost thing is the 1.01 raised to the 13th power. Our raise button, our exponent button, whatever you happen to have on your calculator. And this to the 13th power. Now, we can go further. Actually, let me clear that. Let's open up two parentheses. We'll say 1.01 to the 13th. And then minus 1. Now, you might be worried that the 1 is subtracting from 13 rather than the 1.01 raised to the 13th. Most modern calculators are smart enough that they'll handle that application okay. Close our parentheses and then divide that by 0.011. Close our parentheses again and then subtract our 1. So it's 11.5539. Now, looking at what has to happen here in order to solve for R, which I assume is the payment or the monthly deposit, whatever it is, we would divide this number, 8,000 divided by this number, if we move this one over. Okay. Oops. There you go. And so what we can do is, again, and we talked about this a little bit before, I believe, in the calculator we have this answer button. And so this number, as long as it is already stored in that answer button. So if we want to do 8,000 divided by, and we'll do second and answer. Okay, so I just hit second and then answer. That brings up this same number, so I don't have to write it all down. I don't have to type it again. It's already stored there. Press enter, and now it gives us an exact value. Now, if we just truncated this decimal number after 4 places or so, probably it would be accurate enough, but we want to be sure that we are completely accurate in our answer here. We don't round until it's absolutely necessary. So we end up with 692.40 in that case. Equals R. Okay. So really the key to doing these more involved calculations is really just using the parentheses buttons wisely and nesting everything together, sort of like an order of operations would simulate. So, honestly, I probably didn't need a double parentheses there, because what we could do instead is 1.01 to the 13th. Subtract the 1, close the parentheses, and divide by 0.011. Now, if we didn't use the double parentheses, we could just press equal there and then subtract 1 from that. Okay. But we would need a second set of parentheses if there's like an exponent on the outside there. So I would recommend 2 parentheses open at the start if we have an exponent at the end. So. Which is what we see in a lot of these compound interest problems, because whether it's like a future value or present value, there's going to be an exponent. There's exponents all over the place. So, yeah. Okay. Do you have other questions? So, continuing from Monday, we'll keep going with our discussion of Chapter 2 today, specifically working with the graphs and equations of lines, which again will be significant when we work with linear programming, which I believe is at the end of Chapter 5. forget when that occurs. Chapter 7, it looks like. Which I don't recall where it falls in the book. Yeah, linear programming is chapter 7. So you'll do some of that. I don't remember if you do it you might do it after chapter 5, I'm not sure. So, anyway. So in section 2.2, we've been working some already. We did 2.1 and part of 2.2 on Monday. We've been talking about equations of lines, specifically here. And oh, sorry, I'm on page 85. I believe for homework I gave you problems up through 32. Well, I take it back. I haven't formally assigned it, but that's where I plan to give homework. It's going to sound bad, but I sent an email to your teacher about how we would go about getting the problems to her, like whether I should create them in my Canvas and let her copy it over to hers, or what else. Give her the list of problems, but unfortunately she hasn't responded to me yet. So anyway, next I'll text her, I think. That's actually how we've been communicating most of the semesters, through text rather than email. So. All right. So, yeah, we'll continue on page 85 and work on equations of lines and then parallel and perpendicular lines and things like that. Okay. Now we've looked at a few formulas so far. I just want to recap those. We have slope, which we said was m equals y2 minus y1 over x2 minus x1. We have, for lines, we have the general form, ax plus by equals c, and we also have what's called the slope-intercept form, which is y equals mx plus b. And so last time we saw that, if we want to take something from general form and put it into slope-intercept form, we just have to move ax over to the right hand side and then divide everything by b just to get y by itself. Okay, and then once we get y by itself, whatever number is in front of x, m, remember, is our slope, and b is our y-intercept. And so by that means we were able to sketch a graph of the equations. Just to give an example, just back up just a little bit. Let's suppose that we want to sketch x minus 2y equals 4. by first writing it in slope-intercept form. Okay. So we said we want to solve for y, basically to put it into that slope-intercept form. So we subtract our x over. Again, we want to make sure on the right-hand side we put our x first and then the number second. So it's a little bit counterintuitive, but so we have a minus x first, and this is still a positive 4. The other step is we need to divide everything by -2, and that is to get y by itself. So -2 divided by -2 just gives us a plain y. Negative x divided by -2, I'm going to make that a 1/2 x, and because the negatives cancel, it'll be a positive. But then we have 1x over 2, so instead I'll write that as a fraction, 1 over 2 times x. And then finally 4 over -2, which is -2. So we've got the equation in the correct format, which is our slope-intercept form. And again, our slope is in front of x, so slope is 1/2. And then our y-intercept is -2. Alright, so now we go to sketch our graph. We always start with the y-intercept first, -2, so that's down 2 from the origin. And our slope is 1 over 2, that means we're going to go up 1 and 2 to the right. So up 1, 2 to the right. And we can repeat that as needed, up 1 and 2 to the right. And then use that to sketch in our graph. Okay. So that's kind of where we left off last time, or one of the last things that we did. So the next part, I'm going to kind of switch the order that they do it in the book. I actually want to talk about finding the equations of lines from points first, and then talking about parallel and perpendicular lines second. Okay, so the goal is to use two coordinates to find the equation of a line. Okay, so we're going to start off with two coordinates. Now, realistically, what we need to find the equation of a line is we need one coordinate, so we already have two, so we're ahead of the game there. We need one coordinate and the slope of the line. Okay. Now, if we're given two coordinates, we know we can find the slope just by using our slope formula. So step one is use the slope formula to find m. Okay. So that lets us find our slope. And second, we use the m and either one of our points and this is important. It doesn't matter which of our 2 points that we pick, the equation of the line that we create will be the same. In one case it may require us to simplify more than the other, but it should give us the same equation of the line. This is always a little strange to some students, but yeah, it doesn't matter which point we pick. So basically, the way that we pick which coordinate to use if we're given 2 coordinates is whichever one looks like it's going to be easier to work with overall. Generally that means smaller numbers. So we use m and either one of our points and plug them into what we call the point slope formula or point slope equation. Which is y minus y1 equals m times x minus x1. Okay. So that's our process. And then once we have this, we'll just simplify, and that'll be all we need to do there. Okay. So as an example, let's use the coordinates -2, 5 and 1, -1. So we want to find the equation of the line that contains these 2 points. So what I'm going to do is I'm going to label them x1, y1, x2, y2. The subscripts basically indicate which point they're in. So this is the x and the y from the first coordinate. This is the x and the y from the second coordinate. Now, from there, our slope m we know is y2 minus y1 over x2 minus x1. So we plug in the 4 values in their respective locations. So on top, y2, -1, minus y1, 5. On bottom, x2, 1, minus x1, -2. Okay. And we do want to be careful about our signs because that's going to make a difference. And so we end up with -6 on top, and 3 on bottom, and dividing, that gives us a slope of -2. So now we've identified the slope, and we can use that, and again, either one of our 2 points, to plug them into this formula, this point slope formula. We call it the point slope formula because it involves a point, x1, y1, and a slope, m. It's important to note that we have y and x here. We're not going to fill anything in for the y and the x. That's just our normal variables. It's x1 and y1, the coordinate that we plug in, as well as the slope m. Now, we could use either one of these points, although we've already identified this first one as y1, x1 and y1, so if we prefer, we can go ahead and just reuse that as x1 and that one as y1. It really doesn't matter. These will probably be slightly easier numbers, but in this problem, I don't think any of them are particularly difficult. If we had a term that had like a fraction or a decimal in it, then we might be loath to use that one. But yeah, and a slope may be a fraction as well. That may be an issue. So y1, 5. M is -2. And x1 is -2. Okay. So y minus 5 equals -2 times parentheses x minus a -2. That's just taking m, x1, and y1 and plugging them into this equation. From here, we go ahead and simplify on the right-hand side first. This is -2 times x plus 2. And we could have written that as plus 2. You don't have to take this intermediate step where you write it as minus a negative. So, I mean, it's good either way. If you understand it, I encourage you to not take extra steps, just to simplify the process. We distribute, so it's -2x, and then the -2 times 2 would be -4. Is it hard? I'm hoping it's not that difficult. It's probably strange, but it's not something we do a lot of, but hopefully not too unusual. We get y by itself, and so that gives us y equals -2x plus 1. And that would be our equation. I think the issue and what makes it seem difficult, and this is true for a lot of students at all kinds of levels of ability, is it's just the number of steps and remembering all the steps that need to be taken to get to a solution. Once we do a couple of these, I think you'll feel a lot more comfortable. So again, this is our key formula in addition to the slope formula. So given two coordinates, we start off by finding the slope, just plugging in values and simplifying. Okay. Once we get our slope, then we can pick either one of our 2 points. Now, if we had chosen the other coordinate then instead of the first coordinate, we still would have gotten the same answer. We would have gotten different numbers along the way, but it should simplify out to be the same place, to the same equation. Maybe a little hard to believe at first, though. Now, again, once we had m and then we took one of our coordinates, we plugged that into the equation here. As so. Simplified on the right hand side. And then to get y by itself, we just add them over. I will, yeah, I want to set these up as homework assignments in my math lab for these sections in particular. As I said before, I am working on that. And it may be, she actually gave me her login credentials. It may be that I just have to log into her My Math Lab and set it up myself. That may actually be the solution. All right. Well, let's do another one of these. Okay. Find the equation of the line through 2, 7 and 8, 5. Again, we start with the slope. And I'm going to go ahead and label these x1, y1, x2, y2. It's important that x1 and y1 are the same coordinate, and x2 and y2 are the same coordinate. We can't mix and match there. So y2 minus y1, that'd be 5 minus 7 on top. And then x2 minus x1, that would be 8 minus 2 on bottom. So it's going to give us a negative 2 over 6, which is a negative 1/3. So that's our slope. Next thing is we use our point slope formula, which involves the point x1, y1 and the slope m. We'll go ahead and use this x1 and y1, 2 and 7, and our slope m is negative 1/3. So it's y minus 7 equals negative 1/3 times x minus 2. Slope is negative if we're visually, a slope is negative if it's sloping downward as we go from the left to the right. The downward slope has a negative slope. And if we had an upward slope, this is a positive slope. What do you think would be the slope of a horizontal line? Zero. Good. Yeah, so slope being positive or negative is really just commenting on the directionality of the line. Specifically as it moves from left to right, which is normally how we look at lines, because if we think of this as an application, then left to right, if it's an application relative to time, then we start from time 0 and go to the right. If it's an application based on number of sales, we start with 0 sales and go up from there. So it just depends on what our variable represents in that case. Okay. One last thing here to do is solve for y. So we'll distribute the negative 1/3. So it's negative 1/3 times x. Negative 1/3 times negative 2. Now we have two negatives, so we know it's going to be a positive. And then 1/3 times 2. Remember, 2 is actually 2 over 1. So multiply 1 times 2 on top, and 3 times 1 on bottom. So that is 2 over 3. And it is positive. And our last step is to get y by itself. We'll add 7 to both sides. And so y equals negative 1/3 x. Now here we have plus 7 plus 2/3. So if we want, we can turn that into to a mixed number. Well, it kind of is a mixed number actually. 7 plus 2/3 is basically 7 and 2/3. Because plus literally means and. Like we want to combine these two things together. But it might be better if we want to write it as an improper fraction. So what would, if we have 7 and 2/3, what would be our improper fraction for that? That's correct, Caitlin. I multiplied straight across, so 1 times 2 and 3 times 1, so it's just 2 over 3. (23 over 3). Yeah, if we have 7 and 2/3, then we take 3 times 7 is 21, plus 2 is 23. And then the denominator stays the same, 3. It's alright. It's part of the learning process. (21 over 2). No, but I'm not sure how you would get that. Take this number times that number and add the top number and then divide by the same denominator. So 7 times 3 plus 2 over 3. Hopefully we don't have to work with a lot of these. This equation, it's almost easier to express it as general form rather than the slope-intercept, but generally slope-intercept is the most useful format, so we prefer to use this one. I prefer to use this one, certainly. Gotcha. Okay. Now there are other variations on this that we could work. One variation is they give us a coordinate let's say 1, 5 with slope 3. Okay. So instead of giving us 2 coordinates, they went ahead and just gave us 1 coordinate and the slope itself. Basically what they've done is they've simplified the first part of the problem so we can just get to the second part of the problem. We already know what the slope is, so we don't need the second point. As long as we have 1 point, that's enough to plug into this formula. Y minus y1 equals m times x minus x1. So m is our slope, x1 and y1 is our coordinate. That's a 1 there, sorry. And so we'll plug in these three numbers here, here, and here. Y1 is 5. M is 3. And X1 is 1. And from there, it's now just a matter of simplifying. We already have the slope, so that saves us one calculation. So we distribute our 3. It's 3x minus 3. And then we can go ahead and add 5. So y equals 3x, and that'll be plus 2. That's actually an easier version of the problem because we do already have the slope provided, and we wouldn't have to find it in that case if we already have it. Okay. Next, let's talk about parallel lines. First thing is we need to figure out what we mean by saying that lines are parallel. The geometric definition of a parallel line, or a pair of parallel lines, is that these are two lines that never intersect. So we look at the slope of these two lines. Remember, the slope is rise over run. What would you think is true about the slopes of these two lines? Just by looking at the picture. Positive. Good. So we know both of these lines have positive slopes. Can we see anything more about the value of the slope? Is one line steeper than the other? No, they're not. They actually have the exact same steepness. So what does it tell us about the value of their slopes? The same. Exactly. Parallel lines have the same slope. So if we say two lines are parallel, it means they have the same slope. What's different about them is that they may have different y-intercepts. Like this one has one y-intercept, this one has a different y-intercept, but the distance between the two lines is identical throughout. You know, the rise over run for each line is identical. That's the slope. So in this particular example, not only do we know that both slopes are positive, but they actually are identical. Okay. Now, perpendicular lines. Perpendicular means that they meet at a right angle. So we might have one line that looks like this, and then another line that looks like this, and then this is a 90-degree angle that they meet at. Now we can see with perpendicular lines, we have one slope is positive and the other slope is negative. And in general, we could say that perpendicular lines have opposite slopes, opposite signs. Do the values of the slope look identical? Or do they, like, what I'm saying is, do they have the same rise over run, but one's positive and the other's negative? Or do they even have different slopes altogether? So if they have the same slope, just different signs, we're saying this line is just as steep as this line. We know one's positive, one's negative. But it looks like, just looking at these two, this line looks like it has a more steeper slope than this one has. Okay. Yeah, so I would say that they actually have different slopes. Now, there is a specific way that we can compare the two, or find one from the other. The slopes have opposite signs. We know that's true. And they are reciprocals of each other. So not only are they generally going to be different slopes, we would actually say that they are reciprocals. Reciprocal means that if we take the fraction for one and flip it over, then we get the other. So if this line had a slope of, let's say, positive 2 over 3, what do you think the slope of this other line would have? Negative 3 over 2. Because we change the sign. This one's positive, this one's negative. Absolutely. And then this is 2/3, so we flip that over. This one would be 3/2. Okay. Fortunately, we don't have to do a whole lot with that. This is useful in some regard, but yeah, it's not going to be essential for what we need it for. So, I think the main thing here is that we are able to look and compare directionality, so we know whether something is positive or negative slope, and we can tell if two lines are parallel or not. Perpendicular is a little harder to tell, and as far as lines being perpendicular, this is not anything that there's certainly physics applications here and engineering applications here, but I don't think anything falls in the realm of business in this sense. So we're probably okay without covering that too much detail. Business and social sciences, really, geometry doesn't play a large role, turns out. So, Okay. Yeah, geometry is more essential for people going into STEM fields, less so than in the business and social science fields. So that's why I didn't want to spend too much time on that anyway. I didn't feel like it would be necessarily productive towards our overall goals. Okay, so let's move forward a bit. Now this is a topic that's a little bit outside what we're covering in these sections, but I think it's important overall. And the goal here is to find the point of intersection of two lines. Okay. So how do we know where two points intersect? Excuse me. Get a drink real quick. You can tell it's already fall because my allergies are going crazy. So, which triggers my asthma. So it's awesome times. Anyway, yeah. Every fall and spring. I like the seasons, but I don't like the baggage it carries. So, anyway, so we want to be able to find the point of intersection of two lines. And so, let's say, for instance, we have y equals 2x plus 7 and y equals negative 3x plus 12. Okay, so we want to find the point at which these two lines intersect. Now, graphically, we know that we can sketch these two lines, but unless we're making perfect sketches, it's going to be hard to tell exactly where they meet. For instance, let's see, mark this off. So 2x plus 7, we know that starts at 7. So we go 7 up. And then our slope is 2 over 1. So we go up 2 and then 1 to the right. We draw our line. We have a second line, y equals negative 3x plus 12. We start at positive 12 on the y-axis, which should be my top point here, if I counted correctly. Not always confident in that. Then our slope is negative 3 over 1, because that's what's in front of x, so we go 1, 2, 3 down, and 1 right. Now it appears they meet right here, and I believe that's 1, 9, where that ends up being. But we can't tell for sure from the graph, and in fact I would encourage you not to graph these even at all in the first place. Although the problem is when we look at linear programming, it's based on graphs to an extent, or being able to visualize the information. So, if we want to figure out the point of intersection of the two lines, since we have y equal 2x plus 7 and y equals negative 3x plus 12, the idea is one of substitution, in that we can substitute one equation into the other. So by saying that y equals 2x plus 7 and y equals negative 3x plus 12, if this is what y is equal to, then we can take this expression and plug it in for y in the other equation. And so we would say negative 3x plus 12 is equal to 2x plus 7. And the idea is what's called transitivity, meaning that if y is equal to these two different things, then these two different things must be equal to each other. And if you don't understand that, that's okay. So if we want to think about it as substitution, that's also an equally valid approach. But basically, since y is equal to this expression, we can replace it with that expression in the other equation. Since y equals negative 3x plus 12, we can change y to negative 3x plus 12. Hopefully one of those things makes sense. Now what that does, by plugging that in from one to the other, is it gives us an equation to solve that just has x's in it. Okay? We only have x's, and we have some numbers too, of course, but we should be able to solve this for x. So if we're looking at two lines intersecting, essentially we put mx plus b equal to mx plus b. Okay, whatever the slope times x plus the intercept for one function is equal to the slope times x plus the intercept in the other function, or the other equation. Alright, so to solve this, we need to get x's on one side and our numbers on the other side. And we can go to either side that we please, it's just whatever we want to do here. What steps do you think we would need to do first, let's say? Or what could we do first? There's really not just one step. Yeah, we need to combine our x's. Now, because they're on opposite side of the equal sign, we have to be careful and make sure we do that by taking the opposite of what's on one side. For instance, if we want to take this minus 3x and combine it with our 2x, which we do, because of the equal sign, we can't just add them together. They're on opposite sides of the equal sign, so instead, let's add 3x to both sides of the equation. And the idea is that if we want to move something from one side of the equation to the other, we have to do the opposite. And the opposite of a negative 3x is a positive 3x. Okay. Now, negative 3x plus 3x cancels out. So we just have 12 equals, and then adding here 2x plus 3x gives us 5x, and then we have plus 7. Now we've got the x's together, now we need to get the two numbers together. So what should we add or subtract to both sides next? Then we subtract 7. Good. That way, we have the x's on one side, and our numbers are now on the other side. Our last step then, well, for this part, is how do we get x by itself? You have 5 times x, but we would just want regular x. Divide, yeah. We can divide by 5 on both sides. And so what that means is 5 divided by 5 is 1, so we just have 1x, or x, equals 1. Okay. Now that means that our two lines, they meet at x equals 1, but if we're trying to find the location of the coordinate where they intersect, we have to do more than just find the x value. We also need the y value, because a coordinate is going to be x comma y. Okay? So we know x is 1 already, but the question is, how do we get our y value? Any ideas? Excellent. We use math. Do we have more specific ideas? We plug into the equation. Yeah. And use the same, well, yes. Actually, it doesn't matter which equation we use. This is the beautiful thing, is because this is a point that's in common to both equations. Whichever equation we plug x equals 1 into, we should get the same value for y. So if we plug in x equals 1 to this equation, negative 3 times 1 is negative 3. And then we add 12 to that, so it's positive 9. And we would actually get the same result if we plug in x equals 1 here. 2 times 1 is 2, plus 7 makes 9. The whole goal here is to find the point that is in common to both lines. So if we discover that they have x equals 1 in common, then both equations should give us the same answer for y. So we really only need to pick one to plug it into. And at that point, we just pick the one that looks easier to work with, generally speaking. So yeah, we can say that these two equations intersect at the point 1, 9. Same problem. With two equations. So we want to find the point of intersection, y equals negative x plus 7 and y equals negative 2x plus 9. Now we notice that both of these have a negative slope, -1 and -2 respectively. That means they're both decreasing. The good news is they still have a point of intersection. What we're going to end up looking at is one of them looks something like this, and the other looks something like that. Okay? And so even though both of them are negative slopes, they have decreasing slopes, there still will be a point of intersection where they both cross. Now, we start the same way we did before. We take the mx plus b for one equation, set it equal to mx plus b for the other equation. And again, to solve for x is generally a three-step process here. We get the x's together on one side, we get the constants together on the other side, and the last step is we divide by whatever's in front of x to solve for x. The only question is which side we want to move everything to. And honestly, it could be either one. It doesn't really matter. So what can we do to solve for x here? What can we add or subtract to both sides? Good. X equals, is it 2 or -2? We can add the x. Okay. So we have the x's together, now we need to move one of our numbers. Subtract 9. Let's see, so that cancels the 9, so that is -2 equals -x. And last step, there's two ways we can proceed here. One is operational and the other is logical. We know looking at this, if we want to make this a positive x, we just have to divide by -1 on both sides. And dividing by -1 turns it into a positive x. So x would equal, and this would be a +2. The other one is logical, and that says, if -x equals -2, then positive x would equal +2. I wouldn't necessarily encourage that because sometimes we can underthink some things, but or oversimplify some things, but yeah, it does end up being x equals 2 regardless. Now again, that's just our x value. What's our y value if x is 2? Again, we can plug into any of these two equations. Five, good. Yeah, we take a 2, plug it in here, -2 plus 7. That gives us a 5. That's okay. And again, we actually get the same thing here, so we just pick one or the other. Probably this is the easier one to work with, but we could plug it in here. -2 times 2 is -4, plus 9 does make 5, because it's 9 minus 4. So our coordinate where they intersect is 2, 5. Not really accurate to the drawing, but I just kind of wanted to simulate what's going on here. Alright. So, I don't know how much you're going to need that, but I thought I'd go ahead and introduce the concept here, since it's related to equations and graphs and things. So. Alright. Doing good. Let's move on to section 2.4. Let me make sure I'm not missing anything from section 2, first of all. Probably do not those. I should probably do at least one of these applications, I think. Well, let's look at this 68 and 70 on page 86. Okay. Now here, we're working with this equation, or this data. So data from the Wall Street Journal indicates that the percent change in beer shipments since the year 2007 for Miller Lite beer can be approximated by y equals negative 3.9x plus 27.3, where x equals 7 corresponds to the year 2007. Find the percent change since 2007 that it occurred in the by the following years, and we're going to look at 68, where it's 2014. So, if we're looking at the year 2014, and we know x equals 7 corresponds to the year 2007, what value of x would correspond to the year 2014? So again, x equals 7 corresponds to the year 2007. If we're interested in what happens in the year 2014, what value of x corresponds to 2014 then? Well, if 7 corresponds to 2007, then it must be 14 that corresponds to 2014. In this case, x is basically the number of years into the 2000s, basically. So, if we start counting as the year 2000 as x equals 0, Then 2007 is x equals 7. 2014 is x equals 14. So what we would need to do is take that x equals 14 and now plug it into our equation. So here's our equation. And we said that the year 2014 means we use x equals 14 as a variable. So that all we have to do now is plug in x equals 14. So we'll take negative 3.9 times 14 plus 27.3 negative 27.3. Huh, I wouldn't have guessed that. So that is a coincidence. Now again, what y actually represents here, that's worth mentioning. We need to know the context of the problem. This indicates the percent change in shipments since the year 2007. So that means in 2014 they had 27.3% less shipments than they did in 2007. So getting a negative 27.3 means we have a decrease of 27.3% in shipments of beer since 2007, which is what the equation is describing. Okay. Generally speaking, such an equation is going to be a little bit more complicated than that, but that's the general concept. If we have an equation that models a particular aspect of business, for instance, then by plugging in values, the values generally represent the amount of time that has passed, and it allows us to model what has happened previously and then use that information to predict what will continue to happen in the future. And this model seems to predict that it will continue to decrease, basically. And again, it's not all beer, it's just a particular beer. Okay. Alright, now problem 70 references the same question. And it wants to know in what year will the shipments be down 40% since 2007. Page 86. Okay. So negative 40%, that means we'll take our y equals negative 3.9x plus 27.3, and we're going to take negative 40, and we'll actually plug that in for y instead of x. We remember that x tells us the number of years, while y actually reflects the percent change from the year 2007. So if we want a negative 40% change, then we'll plug that in as our y value, and we want to find out what x is in this equation. So we'll have to solve for x. Notice we don't plug in the percentage, and we don't treat it as a percentage, because in this case y is representing a whole number percentage in this problem. Yes. And that's actually from the question itself that they said that. That's why I didn't write it down. But let me write that down. X is the years since 2000, years since 2000, and y is the percent change in shipments since 2007. So knowing that y has the percent implied already, when they say it decreases by 40%, that means we'll plug in negative 40 for y. The percent is already assumed in this problem. Okay. Now, the question is, again, how do we go about solving this problem for x? Well, it's really the same approach that we've been using, is we want to get the two numbers together, get the x's together. There's only one x, we don't have to do that. And then divide by whatever's in front of x. So, which number should we move in order to get x by itself? Actually, there's technically not a wrong answer here. There's plenty of ways we can move things around. There is one in particular that's going to be easier than the others, and make this problem easier than the others. And so if we want to get x by itself, we can leave it there, move the other number that's with it to the opposite side. Yeah, the 27.3. So let's go ahead and subtract that over. So negative 40, negative 27.3, that's negative 67.3, and then negative 3.9x. Don't let the decimals confuse you. I mean, we treat it the same as any other number as far as how we manipulate the equation. What should be our last step here to get x by itself? Yeah, we'll want to divide specifically by negative 3.9. Yes. Okay. negative 67.3 divided by negative 3.9. Okay, so I get 17 point, let's call it 17.3. We'll just go one other place. Okay. So we get x equals 17.3. And so the question is, in what year will shipments decrease by 40% from the year 2007? So if x is 17.3 and x is the number of years since the year 2000, what year does this correspond to? (2017). Yeah. Now, because our number is a little bit larger, that means it's not at the beginning of 2017, it's about 0.3 of the way through the year 2017. So probably sometimes during the third or fourth month specifically. We should be able to say that. But the question is during what year, and so we would just round down basically, or which is 2017. Any questions there? Okay. I think we'll stop there, and I'll try to get your problems into my math lab today, both for section 1 and for section 2. Now that we've finished both of those, that way you can start working on those over the weekend if you like. I'll give you a little bit more time to turn them in because I know you got problems that you're working on in the other class, but at least a week, I would say, just to give you some time. But anyway, so I hope you all have a good weekend. Good luck with the other class as you move forward. And again, let me know if you have any questions. You can email me or send me a message in Canvas. So you all take care and have a good rest of the day. Bye.